Well, let's move on now to Professor Nigel Brandon. I hesitate to say on a lighter note, but the talk is about hydrogen. Professor Brandon is Dean of Engineering at Imperial College and Director of the UK Hydrogen and Fuel Cell Hub. So we could hardly have a more distinguished or authoritative speaker on this subject. And hydrogen, I think, is rushing up everybody's agenda as we hear the debate about should we buy electric or should we wait for hydrogen. I think probably my diesel car will see me out, but that's not true for everybody. Professor Brandon, please talk to us if you would.
Mike, thank you very much. And can I just check that these are coming up on the screen?
It is, lovely.
Yeah. Okay, you can hear me okay. All right, well look, it's a pleasure to be with you this evening. Thank you for the invitation. I'll try and kind of give a kind of largely an overview presentation, and then we can take perhaps some of the more detailed, if there are more detailed questions in discussion afterwards. Mike, you kindly referenced there the Hydrogen and Fuel Cell Hub, which is a Research Council investment of a number of different universities in the UK, which we lead out of Imperial College, but involves a number of colleagues around the patch. And there's a website. I'll provide a couple of links at the end if people are interested in going and finding a little bit more detail, but it's easy to find if you Google it. I also, these days, I was formerly director of the Sustainable Gas Institute, which is actually a largely industry-funded program at Imperial, looking at the role of gas in the energy system, and particularly the role of challenges around things like methane emissions and their impact on the environment, but also importantly hydrogen. So both of those factors, both of those centres are relevant to today's conversation. And a photograph there of our hydrogen-powered Toyota Mirai, which is a hydrogen fuel cell car that we have at the university. And if anyone wants to talk about real-world experiences of driving such a car, I'm happy to share my own experiences of so doing and refueling it. So what I'm going to try and talk about this evening is I want to spend not too long, but a little bit of time talking about the drivers for hydrogen. And I've worked in this area for over 30 years, and I've seen waves of enthusiasm for this particular topic come and go in the past. And I genuinely think we're at a different place now in terms of our interest, a more informed and perhaps more nuanced view of where hydrogen could play a role and could play an increasingly important role as we look to move to a low carbon energy transition. I want to talk about effectively the three core technologies by which we might produce and use hydrogen. So I'm going to talk about carbon capture and storage. Just going to move my little screen here, which appears to be, oh, no, it's sitting over my, doesn't matter, over my slides, so I can't see the edge of my slides, but anyway. Carbon CCS, fuel cells and electrolyzers. And I want to talk about grey, blue and green hydrogen, or brown, blue and green hydrogen, which you'll see referred to when you read around the subject, which effectively refers to the carbon intensity of the hydrogen that we've produced. And then really talk about hydrogen in the context of its applications, hydrogen for transport, hydrogen for heat and power, hydrogen for system balancing, particularly as we go to a very low carbon system with more and more renewables on the system, and the role of hydrogen for chemicals. And we remind ourselves now that, of course, we make hydrogen today primarily as a feedstock into the chemicals industry. And here we're talking about making hydrogen for very different purposes as a low carbon energy carrier. So this figure is one I'll start off with, and it's really around the drivers for hydrogen. And this is a figure kindly produced by Grant Wilson at the University of Birmingham, and he tracks and makes publicly available these sorts of very helpful charts which plot the flow of energy through the UK energy system. And you can see it's plotted by month of the year and over the last 5 years here. And the red line at the bottom here with the little squiggles on it is the flow of energy as electricity through the UK energy system. And within these lines, of course, are rather important variations on a second by second, minute by minute, hour by hour basis at which we produce and consume electricity. And you see there's some seasonal variation with a bit of a low in the summer months and a bit more of a peak in the winter months. But we're in and around somewhere like 600, 700 to peaking up to 1,000 gigawatt hours of energy is flowing through this particular energy carrier. And of course, we quite rightly are making great strides, and there's been a lot of progress made in decarbonizing electricity. And of course, part of the things we'd like to do is to use that more decarbonized electricity to feed into other parts of our economy. This line in grey in the center here is the flow of energy as a liquid transport fuel. So that primarily means gasoline and diesel. And that's a pretty constant flow, pretty much independent of the season. And of course, there's a lot of interest in displacing these fossil-based carriers with a low-carbon carrier. And quite rightly, a lot of interest in doing that with low-carbon electricity. But just to give a sense of scale, if we were to replace the roughly 1,600 or so gigawatt hours that's in this part of the energy flow completely with electricity, and an electric vehicle is a much more efficient vehicle than a fossil fueled or liquid fueled vehicle. So we might only need to, it might be 4 times as efficient or 3 times efficient. So perhaps if it was 4 times as efficient, it would need about 400 gigawatt hours of electricity. So you can see that 400 gigawatt hours would add on down here and increase our requirement for electricity by about 50%. And then we come to the blue line. The blue line is the flow of energy as natural gas through the UK energy system. And this is in particular used for heat. It's also used for power generation, of course. But the heat flows are really marked by these very quite strong seasonal variations between the summer demand, where the heat demand, of course, is low, and the winter demand, as we can tell today on a cold, dark night. I suspect many of us who have got gas-fueled heatings, and most of us do in the UK, there will be some of you who don't, will have their heating on, and we'll be burning a lot of gas in terms of our national energy consumption. And it's this seasonal variation that actually presents quite a lot of challenges. Firstly, we can see that in terms of the energy flows through the UK energy system, it's gas that carries the majority of the energy today. And while we're making great progress at decarbonising this red line, it's actually the least significant part of the energy flows through the UK energy system. If we want to decarbonise this gas, and let's say we're talking about heat, and we want to electrify that heat supply with, say, a heat pump, and we just simplistically assume, say, a coefficient of performance of say 3, and we see a peak here of about 3,600 gigawatt hours in the winter. And if we meet all of that load with a heat pump, that's going to add about 1,200 gigawatt hours of extra capacity, which more than doubles the current peak in terms of our energy generation capacity, and puts it up to about here. You can also see it generates an even bigger swing between the summer low and the winter peak demand for electricity. And that's one of the challenges that we would have to wrestle with if we were to completely decarbonize using only electricity. So today I'm going to talk about the role of hydrogen and what role hydrogen might play as a vector for decarbonizing some of these transport fuel requirements and some of these heat and power requirements. And therefore, it's very much a synergistic view of the decarbonization of all of the energy carriers, both gas and electricity. There is another driver for hydrogen beyond carbon, and that's air quality, particularly in a transport context. Now, this is a somewhat old map, but it's the sort of nicest looking map. I don't think it's got any better since 2008 significantly, but these are NOx map of London. This is Heathrow Airport out here. I happen to be living down in this little bit, which isn't quite so, doesn't have such quite high NOx emissions. But the NOx emissions track the main arterial routes through London. And so London is regularly, as are other cities in the UK, regularly in breach of air quality regulations in terms of NOx emissions in particular. And if we had, of course, electric transport, whether that's a battery electric or a fuel cell electric vehicle, our NOx emissions come down markedly, and we lose and mitigate some of these air quality concerns and their associated impacts on human health. So let's come back to hydrogen then. And this is a sort of cartoon of why we think about hydrogen and why hydrogen might be interesting. And the first thing I want to make very clear is that today we're not really thinking about hydrogen as the energy carrier. We're thinking about hydrogen as a energy carrier. So it will have a role to play, but it won't have a role necessarily everywhere. But why is hydrogen interesting? Well, once we've made that hydrogen molecule, it doesn't carry a carbon molecule with it. If we convert that hydrogen, whether that's with a fuel cell or whether that's in a combustion engine like a gas turbine, the product of that reaction is going to be water, and that of course is not going to have any associated contamination or health implications. We can make the hydrogen from fossil fuels, and this shows us hydrogen here, water here combining with methane, the primary component of natural gas, through something like a steam methane reforming reaction, a high temperature thermochemical process, which produces CO2 and hydrogen. And this is the way we make hydrogen today. We make it in steam reforming reactors on a large industrial scale, but we do not conventionally, of course, capture the CO2. So if this is to be used to make hydrogen, and now it would make hydrogen in which we would need to capture that CO2 and store it in something like a carbon capture and storage scheme. So this makes so-called blue hydrogen, helpfully colored blue on the diagram here. That is hydrogen made from fossil with CCS. So it's a low carbon, but not a zero carbon hydrogen. We can also make hydrogen from electrolysis, and a lot of the excitement at the moment is around this form of hydrogen, so-called green hydrogen. It's green provided we get our electricity from a low carbon source. So if we have electricity from renewables, whether that's wind or solar, and we can put that into an electrolyzer, we'll talk more of that in a minute, then we can make hydrogen which has no associated carbon footprint, assuming that we haven't got a carbon footprint with the electricity supply, and that will make a so-called green hydrogen. We can then put take that hydrogen and put it through something like a fuel cell or a gas turbine to turn it back into electricity for power. We can take that hydrogen, and if we wish to, though I'm not going to talk about this really today, we can take it with sequestered CO2 and we can methanate it, and we can make effectively a low carbon or a recycled, in carbon terms, methane. We can take that hydrogen and feed it, either blend it back into the gas network with natural gas to lower the carbon footprint of natural gas, or we can use hydrogen as effectively pure hydrogen and put it into these different sectors. And we'll talk about the chemicals, the transport, and the heat and power sector today. So that's the kind of overall picture for the role that hydrogen can play. So as I said, you've got what people talk about, these three different colors of hydrogen. Blue hydrogen, that's hydrogen made from fossil fuel, gray hydrogen, that's hydrogen made from fossil fuels. 96% of the hydrogen we make today is like this. It's unabated fossil, and we make it for the chemical sector, for fuel upgrading and dehydrogenation reactions and so on, hydrogenation reactions and so on. Blue hydrogen is hydrogen made from fossil fuels with CCS, and green is hydrogen made from renewables. So these are effectively coupled with fuel cells, if you like, the main hydrogen technologies that we'll just very briefly touch on. So this is my only slide on carbon capture and storage. If anyone is interested in more details on CCS, we produced a report through the Sustainable Gas Institute a few years ago now, but it still gives you the basics and a bit of an update on where the technology is today. And in a CCS technology, we're taking something like coal, or we're taking natural gas. We're going through various industrial scale thermochemical processes, adding in steam and producing a mix of hydrogen and CO2. We're capturing that CO2, and then the hydrogen is going forward. So this is never 100% effective. You can capture perhaps 96% of the CO2 if you do it with modern technology. But nonetheless, therefore, it's a low carbon but not zero carbon hydrogen that results. Happy to take questions on electrolyzers if people are curious about the details, but broadly speaking today, there are two commercial electrolyzer technologies available. That's alkaline electrolyzers, which we've been a mature technology set that we've been using alkaline electrolyzers for things like chloralkali cells and water splitting for over 100 years. You can go and buy a 100 megawatt electrolyzer if you want from people like ThyssenKrupp. So it's a mature technology set and has some advantages and some disadvantages. It's the lowest cost route to green hydrogen today, but it's quite a large plant. It's quite big. It doesn't produce hydrogen at particularly high pressure, which some applications need, and it's not particularly it's not particularly flexible in its load following characteristics, more of a base load type technology today. PEM electrolyzers are a relatively new game in town, but are increasingly being commercialized. We have a very good company in this space in the UK called ITM Power, based up in Sheffield. They use a polymer membrane as inside the electrolyzer. They need precious metal catalysts, however, like platinum and iridium, but they are more flexible. They produce hydrogen at pressure. And if you go and drive your fuel cell car onto the Shell forecourt on the M40 or onto the at Beaconsfield or on the M25 at Cobham, it will be an ITM polymer electrolyzer that would produce the hydrogen that would refuel your vehicle. And then the technology I'm particularly interested in, but is embryonic still, only one company will sell you one of these today, and that's a German company called Sunfire. This is a high temperature electrolyzer. It runs up at nearly around 800 degrees C. These run at much more ambient temperatures. And that has a much higher electrical efficiency. It can utilize heat as well as electricity to produce to produce hydrogen. And these electrolyzers can deliver you well over 90% efficiency, whereas these lower temperature electrolyzers today are around 65% efficient in terms of electrical work into hydrogen out. So those are the sorts of classes of electrolyzer technology. And then you may well ask the very good question about cost. This is from a recent report that ARENA have issued. It's only out in the last few weeks, so it's the sort of most up-to-date perspective on hydrogen costs. And these are the hydrogen production costs in US dollars per kilogram of hydrogen. Based on this review, you will see a range here. And the reason there's a range is that the cost of hydrogen produced by electrolysis is very sensitive to the cost of the electricity. Around 60 to 80% of the cost of green hydrogen is the cost of the electrons. And so it's very sensitive to that price, and therefore very sensitive to the renewables price that you're feeding into the electrolyzer, and therefore will vary depending where you are in the world. We should be very clear now that green hydrogen is the most expensive form of hydrogen today. It's significantly more expensive than blue hydrogen, and blue hydrogen is reasonably more expensive than unabated fossil-derived hydrogen. But as we start to look at cost projections like this, and I'll show you another slide in a moment based on another study that that's been done in the UK, we start to see really ambitious anticipated reductions in the cost of hydrogen as we look out towards 2050, run from a number of factors, but in particular run from the reduction in the input price of electricity. So assuming here from 53 to 20 US dollars per megawatt hour, for example, as the price of renewables continues to fall. Some wins in electrolyzer efficiency, which helps reduce the capital cost, and then some minor reductions in price based on improvements in lifetime and so on of the electrolyzer itself, some improvements in the cost of borrowing money because of the risk profile of the technology as it matures, leaving you into a kind of $1 US dollar per kilogram of hydrogen price. Now, this is a very competitive price indeed, and would make this sort of technology completely cost effective relative to other energy carriers. But that's quite a journey to go down. We did some analysis in the UK. The Offshore Renewable Energy Catapult led this analysis, and this was some slides I was involved in helping to present to the UK Parliament Environment Audit Committee last year. This is a kind of 2030 view on green hydrogen. So now we're at about what, just 2.2 pounds per kilogram. So that's about what, 3.5 or so, $4 a kilogram. So where are we? We're up around here. So that's consistent. And with the projections of coming down to perhaps 1.5 pounds, so perhaps $2.50 per kilogram of hydrogen in 2050. So not as bullish as this, but still coming down the cost curve. And those cost downs are sensitive to, again, to the price of the electricity that's being fed in and the efficiency of the electrolyzer. So we'll perhaps talk about that in Q&A if people would like to, but there are prospects and lots of commentators feel that by 2030, green hydrogen will be the cheapest form of low carbon hydrogen, cheaper than blue, with the prospects for further cost down going forward. And the other technology I want to talk about is one I've worked on for a long time, which is fuel cell technology. So if we've got hydrogen, the most efficient way of turning it back into electricity, if that's what we want to produce with it, is in a fuel cell. And there are, broadly speaking, two types of fuel cells. Well, there are a number of types of fuel cells, but there are two leading, I might say leading candidates in terms of the current fuel cell sales worldwide. A technology that has been around for a long time, the fuel cell, but it's taken a significant time for it to become a commercial proposition. But in 2019, over 1 gigawatt of fuel cell products were shipped worldwide. So it's starting to move into more serious territory. There are two main classes here that I want to talk about: the polymer fuel cell, the proton exchange membrane fuel cell. All fuel cells run on a similar principle. They have an ionic conductor, which separates two electrodes where the electrochemical reactions happen. In a PEM fuel cell, we put hydrogen on one side. That hydrogen is oxidized, releasing electrons, forming protons. Those protons cross the membrane, which is permeable only to protons. They combine with oxygen at the air electrode, plus the electrons that are transported around an external circuit and produce water. That flow of electrons is electricity, and the fuel cell would generate you about 1 volt if no current is being drawn, and about 0.7 volts per cell when you are drawing current. So that's how the fuel cell works. It doesn't rely on raising heat. It's not like a heat engine, and that means that it's fundamentally a very efficient way of converting a fuel back into electricity. Indeed, you would reasonably expect even a small fuel cell of, say, 1 kilowatt in size to be 60 to 70% efficient in terms of turning fuel back into electricity, which is about as good an efficiency as you can get from a very large combined cycle gas turbine thermal power plant. The other type of fuel cell, which I'll talk about today, is the solid oxide fuel cell. This uses a different set of materials. So in the low temperature, we use a polymer membrane, as the name suggests, normally a perfluorinated sulfonate membrane called Nafion. In the high and electrodes that contain precious metal catalysts like platinum. In the high temperature fuel cell, which runs somewhere between 600 and 800 degrees C, whereas this runs around 100 degrees C, we use different materials. We now use ceramic materials. The electrolyte now conducts ions of oxygen, but again, we put hydrogen or a hydrogen-rich gas on the fuel side. Again, the fuel is oxidized, releasing electrons by accepting the oxide ions to form water and now steam at these temperatures. And on the air side, the oxygen is reduced. And again, we get the flow of electricity, which is flow of electrons. Okay, so those are the brief sort of introduction to the key technologies. Let's talk a bit about the applications. And hydrogen for a long time has really been associated with transport. And if we look back at the last wave of enthusiasm for hydrogen, which was in the 90s and the noughties, it was really motivated by hydrogen fuel cell cars. So light duty vehicles. And here we, of course, have our hydrogen fuel cell Mirai. There's a new Mirai just coming out. A limited number of these have been manufactured. About 11,000 have been purchased, and 180 have been purchased in the UK, which is as many as Toyota made available to the UK. And it's a very nice electric car to drive, right? So this car, the cartoon on the side is actually a map of where the components are, the hydrogen tanks inside the vehicle under the floor, the fuel cell, which produces just over 100 kilowatts. So it's an electric car that will do 340 miles. You can refuel it in a few minutes, and it's a very effective, a nice car to drive. The Hyundai have just brought out a new fuel cell electric vehicle, the Nexo, that costs you £70,000 to buy. So these are currently still not cheap motor cars. But the new Mirai will be coming later this year. That will do you 400 miles and cost about £50,000. So still quite a lot for a Toyota, but much less than they were not that many years ago. So a lot of interest still in fuel cell electric cars, but we might want to talk about it in the discussion. But I have to say, as the vehicle size gets smaller, battery electric really starts to look more attractive perhaps than hydrogen fuel cell electric. But as the vehicle size gets bigger, the converse is the case. And here we see, I think, one of the really interesting areas for fuel cell vehicles, which is the bus market. We have a number of these buses in London. We've had them for a while now, which run on this route through Covent Garden. They're refueled actually at a refueling point out near the Olympic Park in East London. Aberdeen has these buses. I believe they're coming into Birmingham as well. So effectively zero pollution public transport, which is what these bus fleets offer. And you'll see there quite ambitious programs about hydrogen fuel cell bus rollout, particularly in Asia. And here we can see Shanghai. We've just heard a little bit about Shanghai from our previous speaker, but China, very ambitious plans around these sorts of transport technologies, but also in South Korea and in the US and in parts of Europe and even here in the UK. I do think this is a really interesting market for hydrogen fuel cells. The other really interesting one, I think, is when we come into other heavy-duty vehicles like trucks. As soon as the energy requirement for the vehicle starts to increase, it gets much harder to deliver that with batteries. And using a fuel cell in a hydrogen tank starts to become more attractive. And as we've made our national and international commitments to net zero, how we decarbonize long distance transport and heavy duty transport is really putting hydrogen fuel cells back onto the map of both the vehicle OEMs and companies involved in the truck sector like Toyota and others. So we have a number of, if you like, smaller duty vehicles and heavier duty, larger vehicles, increasingly of interest now, which are hydrogen fuel cell powered. And then finally, I think one perhaps we hadn't, those of us working in the sector, seen a few years ago, which is hydrogen fuel cell electric trains. There is now the world's first fuel cell passenger train operating in Germany. You might have seen there was a piece on the BBC actually about the University of Birmingham and others doing the first tests on the UK's first hydrogen fuel cell electric train. So this is about electrification of train lines to replace diesel electric on lines that don't carry sufficient passenger numbers to warrant the cost of full electrification, but where we still want to move away from diesel. And this is proving a very interesting opportunity for the right sort of application areas such as that. And again, in terms of the refueling issue, it's nice and straightforward. You know where the train goes from and to, and you can manage that refueling infrastructure. Okay, so I want to move on then to some of the other application areas and talk a little bit about hydrogen for heat and power. As I said, as we saw in the figure earlier, hydrogen for heat is a really difficult, or heat is a really difficult topic for when we come to decarbonisation. These seasonal variations between winter and summer, our very strong reliance on natural gas, which is inconsistent with our decarbonisation objectives, means that we need to find an alternative. Heat pumps and electric solutions are in fact ideal for new build, but are quite difficult as a retrofit into our largely old and quite leaky housing stock. This shows the penetration of households connected to the natural gas network in different parts of the world. And the UK has the second highest penetration after the Netherlands, with around 85% of our homes connected to the natural gas network. So for us, this is a very big challenge, but also an interesting opportunity. But you'll see other countries that you can spot on there, the Netherlands, Italy, Singapore, Australia, and so on, who have high penetration rates. Now, Japan has been looking at this for a long time, and this is a cartoon of a Japanese home. in this case still operating on or in fact on some form of natural gas, but in the future could also operate on hydrogen, in which they have a fuel cell in the home that takes this gas and turns it into heat and power and couples it with other sorts of renewables. And obviously, if our fuel cell is taking in natural gas, it's not a zero carbon home, but it is a more energy efficient home and one that could use hydrogen in the future. And 300,000 of these so-called fuel cell micro combined heat and power units, so that's a fuel cell that generates both electricity for the home, but also captures that heat locally and uses it within the home to give you a much more efficient boiler, essentially, have now been purchased by consumers in Japan, for example. Now, I want to here dwell unashamedly on some of my own work in this area. So some years ago, over 20 years ago now, we set a company up based out of our research at Imperial College. This company was called Ceres Power. It now goes by often the name of Ceres. It's simplified its name. And it's a fuel cell company that's based in the UK. It's based in Horsham, which is to the south of London, and is producing a fuel cell technology, which is targeted in part at this application, but also in other a range of applications. These slides are taken from the annual general meeting that was held in December. So I've lifted the slides and they're all publicly available on the company's website. And it tells you a little bit about it. Interestingly, for those who follow these things, the market cap for this company in December was 1.8 billion. The market cap today is 2.5 billion. So it's fair to say it's a fast moving sector. It's also disappointing I don't have more shares. So just to sort of give you a sense then of the movement in the fuel cell sector, which is proving a very dynamic sector in general alongside the hydrogen sector. And this is Ceres slides. So the key thing is this fuel cell, which is a very innovative approach that we invented at the university all those years ago, but is now really the company has taken forward the processing and the manufacturing of this, of which there's a huge amount of know-how and IP to actually produce this in volume. And now you can now buy this embedded in a fuel cell product in Japan for the commercial 4.5 kilowatt CHP market. Bosch have taken a significant stake in the business and are interested in putting this technology into a range of applications like EV chargers and data centers. Weichai in China are taking this technology and putting it into buses and trucks, not as the engine, but as the auxiliary power unit on that bus to make a hybrid bus. And there's just been a new partnership announced with Doosan in Korea, taking this up to the hundreds to kilowatt to megawatt scale for power generation. So this is a British company pioneering a fuel cell technology, but with significant international uplift, significant international attention. And these again are from the company. It just shows you, this is the photograph of the CHP unit in Japan, for example, and some of the pictures of some of the technologies that's being developed. So I want to then move on to the system balancing point. I'm conscious of my time, and take a slide that one of my colleagues has kindly produced. Professor Goran Strubat. Goran is a power systems engineer, and he's interested in the economics of power systems from a kind of engineering as well as policy and business perspective. And this is a graph he shows, which looks at, for example, the value of flexible technology and the need for system balancing. So this is looking at the UK energy system, and he's modeled here, and his colleagues have modeled increasing penetration of wind generation onto the UK electricity system up to 30 gigawatts, which is this, easily within the range of numbers that are being projected for offshore wind. And the percentage of wind that would be curtailed if nothing else was done to manage and to balance the supply of energy demand. So significant curtailment of some of that installed asset. Another way of looking at it is the utilization of the infrastructure that's had to be built. If we simply go with a solution in which we balance supply and demand in an unintelligent way, simply by increasing the amount of infrastructure, the amount of wires we have to carry the increasing peak loads without trying to time shift or in other way manage the, as I say, the peak with the peak in demand, with, for example, with the peaks in generation or the lows in generation. And this gives us an expensive infrastructure, which we also utilize less, and therefore is quite an expensive proposition. So his work shows that there is a value of well over £8 billion a year to the UK economy for flexible technologies like energy storage. And that can be addressed in a variety of ways, and batteries, of course, are part of that. But so is hydrogen, or at least so is potentially hydrogen. And this is some of his analysis for hydrogen reserve needed to deal with the low wind period. So some of you might know that in the winter months, we often get a period in which the wind does not blow for several weeks in Northern Europe. And this looks at the number of weeks with low wind and the sort of reserve you would need to be able to address that shortfall in generation without relying on fossil fuel reserves to so do. And you can see that it comes up into very large numbers. These are in terawatt hours, and a 4-week period with low wind in February, for example, would need something like 20 to 40 terawatt hours of energy storage. That's very, very, it's almost inconceivably large for battery-based storage. But you can start to think about underground storage of molecules like hydrogen and putting that into something like solution mine salt caverns. That might sound a bit far-fetched, but we already do it. We do it for natural gas extensively. We store about 10 terawatt hours of natural gas in the UK, and we also store hydrogen, mainly for balancing, for load balancing on chemical plants. And the largest single store in the US holds 100 gigawatt hours of hydrogen, for example. So these are of interest for these more strategic reserves to balance supply and demand. Finally, I just also want to mention, this is our latest spin out. We've just formed this company a couple of years ago. It's a flow battery business. It uses a flow battery as a type of battery in which you store your energy inside a redox couple. So you have a cell in the middle here into which you put electricity when you want to charge the battery, and will convert those what you've produced back into electricity when you need to. Conventionally, these use 2 tanks of a liquid, normally a vanadium redox couple, which you produce an oxidant and a reductant and store those. That has the advantage that when you want to store more energy, you just need a bigger tank. So scaling this to quite large, for example, to 12 hours of energy storage becomes a much more cost-effective proposition than with a conventional battery. And what we have done is invented some new chemistry, which is much cheaper than vanadium. It uses manganese as the liquid redox couple, and it uses hydrogen, actually in a closed loop, in a fairly low pressure tank as the other redox couple. And we believe this gives us a number of cost advantages and integrates nicely as well with the hydrogen economy. This got to the Shell New Energy Challenge final, which was held just before Christmas, came second, sadly not first. But we're still hoping to take this forward. And we have a startup now with based in their own premises in West London. So finally then, just a couple of examples from the chemical sector. These are a bit wordy, but I'll whip through them. Chemicals is really where we use a lot of hydrogen today. So ammonia is a good example, accounts for 1.4% of global CO2 emissions. Hydrogen is the primary component of those CO2 emissions. 6% of natural gas and 2% of coal is used for hydrogen production for the chemical sector. So people are increasingly interested in moving to green hydrogen to displace this fossil-based hydrogen for chemicals. I thought, again, a bit wordy this slide, so I apologize, but there are some big projects around, even during the pandemic. 100 megawatt electrolyzer project in Germany, for example, looking to make renewable methanol. This program with Shell in Rotterdam, where they're taking wind power to make hydrogen to help decarbonize some of their chemicals facilities. And what was until very recently, when it was overtaken by an Australian project, the world's largest green hydrogen project in Saudi, taking very low cost wind and solar through electrolyzers to make green hydrogen and green ammonia, and then shipping that to end markets to convert the ammonia back to hydrogen. So I'll leave it there, and I'll leave up some web links. If you're interested, we have our Hydrogen Fuel Cell Supergen web link, the Sustainable Gas Institute, We also have an Energy Institute at Imperial, which looks at a wider range of issues if anyone's interested in following that. And we do run our own consultancy in this space, should anyone have any interest in reaching out to us. So I'll stop there, Mike. Thanks. I think I'm going to stop sharing.
Well, Professor Brandon, that was absolutely great. Lots of new things in there for us to digest. As usual, we've got a slew of questions, so I'll do my best to read them out without too much editing. A question from Victor, which says, I'm interested in using the gas grid with hydrogen for domestic heating. Can you comment on the risks arising from metal embrittlement in the pipe runs? Yep,
I mean, it's a very good question. And I'll talk about that in a couple of ways. So firstly, of course, hydrogen is known as, can embrittle metals, as well known. I think it can also leak. Hydrogen is a very small molecule. It gets out of little places that other things can't. So in terms of the switching the gas network to hydrogen, I guess a couple of things to say. Firstly, the UK has been relining its old cast iron low pressure distribution system with polyethylene piping for some years now. Some of you might have noticed holes being dug up in the road with reels of yellow pipe next to it, and that's a group of folk putting in that piping into those gas distribution systems for the sole purpose of reducing the amount of methane that leaks, which is a good thing from a safety perspective and a good thing from an environmental perspective. Now, that polyethylene happens to be a perfectly safe carrier of hydrogen, so that is quite convenient. There is work going on, led by the Health and Safety Lab, to confirm that this can be done safely, that hydrogen can be transported into people's homes. There's a trial program in Kiel at the moment, where there is a microgrid of hydrogen being tested and evaluated on campus, where they have actual buildings that have all been converted. These are buildings where staff live, but they've been converted to run on hydrogen, to check that that can all be done safely, that the fitters, the engineers, the service engineers can safely install. You can imagine that you probably need to make certain that your pipe fittings are completely secure if you're going to be putting hydrogen through them. So that's all happening at the moment. There's no reason to think that can't be done, but quite rightly, the health and safety labs are confirming that that's the case. In terms of the higher pressure mains, then that's perhaps a more open question, right? So I don't know how many of you follow how the gas distribution system runs, but there are some big, very high pressure transmission lines which then drop down in pressure, and then those drop down in pressure again before they come down to your home. Those high pressure lines, you might think, would have more risk of embrittlement. It's not my area of expertise, but I have spoken to colleagues who work in the sector, and they are reasonably sanguine that that won't be an issue, but it's fair to say that there's a testing program and a development program going on to confirm that you could use those high pressure mains safely on hydrogen as well. But at the low pressure end, the pipes that go into your home, I think there's a lot less concern, and there is a program of work going on to confirm that these things can be done safely at the moment. Great, thank you. I've got one more related question, then I'll go to Bill Wicksteed, who wants to be on the telly. I remember reading in that hydrogen in a BMW tank would evaporate if parked for a few days. Is that still true? Well, that was a program that BMW ran some years ago. It used liquid hydrogen. The challenge with liquid hydrogen is it's very hard to stop any boil off, because there's such low temperatures of that liquid hydrogen that if there's any heat, and it's very hard to stop any heat getting through and causing boil off. So indeed the case that if you park a liquid hydrogen tanked vehicle for a long period of time, the hydrogen would all boil off and dissipate. And no one is really considering using liquid hydrogen today for passenger vehicles. There may be an opportunity to consider liquid hydrogen for, if you like, more commercial applications. Aircraft, for example, are of interest as a potential liquid hydrogen, and also some aspects of shipping. But the fuel cell vehicles that I showed there either use 300 bar hydrogen in the bus or 700 bar hydrogen in the Toyota Mirai, which is a compressed hydrogen, and you don't get the boil-off issues with the compressed hydrogen. You still have to engineer a completely safe tank, of course, and there's been a lot of work done on that. And in fact, the most expensive part of that car is the hydrogen tank, not the fuel cell now. But that's because they're made in low volumes by aerospace type grade technology, and the automotive companies are very confident that if they wanted to go to volume production, they take an awful lot of cost out, because there isn't, I mean, the intrinsic materials costs are not high. But liquid hydrogen, I think, is, yes, it's the case for the BMW, but it's not the technology that we're pursuing for those applications today.
Very clear, thank you. Bill Wixty, please, on screen.
I wanted to go on screen, not because I think I'm pretty, but because I wanted to say what a wonderful talk it was.
All right, thank you very much.
Really good, understandable even to an economist. I was particularly fascinated by the point that was made in your later slides. I think you showed Professor Goran Strabach, whose name I can't pronounce, and to wonder two things about the storage you described. First, obviously, if you've got salt mines, you can do it. Is it something we can manage across the UK, or is it rather geographically specific? And secondly, bearing in mind the paranoia that arises in the planning framework every time we try and do something that looks different, what's the above ground shape, noise, and other characteristics that are liable to fall foul of the planning system?
Yeah, both very good questions. I mean, the UK is blessed actually with a lot of capacity, that we have a lot of geology that would be suitable if we chose to do so for solution mining for hydrogen storage. Actually, we're very fortunate in that regard. And these are going to be, if that's what we choose to do, as part of a package of storage technologies. I mean, we'll need a variety of different types of energy storage, ranging from an hour by storing for an hour to perhaps buffer on the low voltage distribution system for your peak loads for your electric vehicle charging and things like that, which are going to be much more likely to be conventional battery based solutions, through to perhaps overnight 8-12-hour energy storage, which might be, for example, that flow battery solution that I suggested, but there are other technologies as well. Through to, if we're going with hydrogen, that's more likely to be at the sort of weeks of energy storage, so more strategic storage, and you won't need that everywhere. You'll need it in a relatively small number of places. So the fact that we can't put it absolutely everywhere is less of a concern, provided we can put it somewhere. Those would be then pipeline connected in the same way that we have pipeline natural gas. And indeed, you'd intend to try and repurpose that gas network to being a hydrogen network in the future. The natural gas network will not have an obvious role to play in a world in which we are trying to hit net zero. The only role it might play is if it is coupled with carbon capture and storage for, say, large-scale power generation. Or it could be coupled for large-scale blue hydrogen generation. But we're not going to be able to put natural gas for space heating into buildings. It's going to be inconsistent. So we will either have to go all electric, which has its own very significant challenges, or think about a low carbon gas like hydrogen. So it will be and in terms of what the impact are, well, it'll be a similar impact to the gas network we have today, right? I mean, if we move hydrogen down an underground pipe, so it's not got the same challenges, for example, as putting in electricity transmission cables and things like that. The technologies that make it don't make any noise, because if it's an electrolyzer, it's just a box that doesn't have any mechanical components. If it's going into a fuel cell, well, that has a fan. It's about as noisy as a desktop computer. If you're putting it into a gas turbine, then you've got the noise of a turbine. But those are sounds, and we're familiar with, and we can mitigate against. So there aren't big There shouldn't be. Now, it shouldn't be big factors. I said the only factor one would have to bear in mind, certainly at the moment, is that planning permission for a hydrogen refueling point for if you want to go and build a hydrogen refueling station for your car or for a fleet of vehicles. At the moment, planning rules require quite a big area around that hydrogen refueling point for safety reasons, because these are still early stage technologies. That means you need quite a big footprint. So you tend to find the hydrogen refueling stations, as I said, at the moment, you can go and refuel in London, you can go and refuel at Heathrow Airport, you can go and refuel at Gatwick Airport, you can go and refuel on the M25 at Cobham, you can go and refuel on the M40 at Beaconsfield. Then the next one after that is, there's one in Sheffield, they're building one in Birmingham, and then you start to run out of hydrogen, and even though you can go 300 miles. So, but they tend to be out of town. So the question is, what do we need to do to be able to make these more compact so we can put them into urban centres? And that's a planning issue, which is more about, it's the safety case planning issue. And of course, understandably, if people can get, one can get scaremongering and so on around these things. I do not want a hydrogen station next to my school type of thing, which you can find for any new technology. So you've got to be careful to get that right.
Mike, can I ask a very brief corollary?
And by all means, Bill.
Climate change and the irregularity of our climatic patterns, does that further underline the desirability of using hydrogen as a storage medium, which will make green electricity generation it's viable?
Yeah, I mean, we're only really having this conversation because of concerns about CO2 emissions. The hydrogen as a low carbon carrier becomes important when we're trying to decarbonize all of the economy. And if we're trying to decarbonize all of the economy, that means we need to decarbonize air travel, long distance transport, industrial heat, steel making, cement making, all of these things which are actually really hard to do. And it's when we come to this, the chemicals industry, it's when we come to this sort of area that we start to think about using hydrogen. I just sort of make the point, right? If we're going to make, the driver for decarbonisation is going to be renewables. Now, nuclear may well have a role to play. Happy to discuss it, but certainly in most places it'll be renewables, and that's going to make low carbon electricity. And so the first thing we should do with that low carbon electricity is keep it as electricity if we possibly can, and use it as electricity where we can. But for some of these applications, that's a difficult thing to do. Either the electricity is not ideal, or it's made in places which are a long way from where we need it. And under those circumstances, or we haven't got a technology that can store enough of it, like for a long distance truck or an aeroplane. Under those technologies, then, under those circumstances is where you think, well, I might take that electricity and make it into a molecule, hydrogen, that I can then move and store much more easily than the electricity. But I pay a penalty for that, right? I pay a cost, financial cost. I also pay an efficiency cost. So if my electrolyzer is 70% efficient, I'm rejecting 30% of that energy stream. But if that's the best way to use it because of the end user requirements, or because we can't use it in any other way, then it's a sensible thing to do. So it's really when we start to look at the totality of the picture that hydrogen becomes part of the picture. And that's really what I mean. I think it's a more nuanced and informed view. It's not saying, well, it's got to be hydrogen or it's got to be electricity and the two are fighting with each other. It's actually how they work together that's important. And that's where ammonia comes in, because there are also very strong advocates for taking that hydrogen and turning it into ammonia. Now that is another step in the process. You degrade your efficiency further. You add more cost. But if you're going to make hydrogen in the desert of Saudi and you want to ship it to the energy source, you want to ship it to Northern Europe, you're not going to do that. Liquefying hydrogen is a difficult thing to do. So that's where ammonia might come in. And we might start to see a traded market, not in LNG, but in liquid in ammonia. And then that ammonia being cracked. So we might see a very different, and that's why countries like Saudi Arabia and Australia now are investing in these technologies because they don't want, you know, they can see the writing on the wall. They're not going to be a fossil fuel producer, but they have very low cost renewables, but not near a market. So there we are. That's the kind of overall picture that's emerging, and it's one of the reasons why just in the last few years we've seen really a surge of interest in these technologies.
Fascinating, thank you. I've got a couple of questions, one which are very similar, one from an anonymous attendee, we don't know who they are obviously, and another from Tony Bishop, who I think knows this industry quite well. What about aircraft? You did touch upon this, Professor Brandon.
Yep. Well, look, aircraft are probably one of the more difficult application areas to decarbonize. It is true that people have made, you know, battery planes that will take off and fly, and of course they can. And you are starting to see plans now for hydrogen fueled planes. My own view is that the aircraft market is probably the toughest one of all. It's the hardest one to decarbonize. It's the area where we need the highest levels of energy density on board the vehicle, the plane. So perhaps we'll be able to do that with hydrogen, but my personal view is that if we're going to ever make synthetic so-called e-fuels, in other words, we're going to take electricity and we're going to go through a set of steps which involve making hydrogen, by the way, and we're going to take CO2 and turn it back into a synthetic liquid fuel, that we should put that, and we're going to use that, we should put it in an aircraft, because that would give you the energy density whilst also mitigating the carbon intensity. But it will be an expensive fuel. But perhaps for air travel, that's what we should be doing. But you certainly are seeing programs emergent now in hydrogen as a potential aircraft fuel. It's this trade-off of, well, you know, the challenge with hydrogen is it's really tricky to store in a small space, right? Its volumetric energy density is a challenge, right? Better than a battery by a long way, but still not as much as we would like as a liquid fuel. So there are routes to dealing with decarbonizing the aircraft industry if we go down these liquid e-fuel routes. But hydrogen's on the table, but I think it's not the first place I'd look to use it.
Great, thank you. Robert Whitfield is on screen, please.
You're on, Robert.
Ask a question about heating, domestic heating. And I'm one of those people in the 15% who are not on the gas grid, and nobody talks about us. And what we have had is oil in tank. We've moved towards heat pumps, but and the system is designed for heat pumps, but we would need something to top up the high temperatures, and I've been looking for that to be hydrogen. How long will I have to wait? Is it forever for a hydrogen tank to replace an oil tank?
It's a good question, isn't it? And I think the idea of kind of hybrid heat pumps, which is what I think you're talking about, so this is a combination of gas and electricity working together, are actually a really interesting technology, particularly in the UK context, where we do have these quite high heat demands in terms of some of our older or larger buildings that have quite high heat demand. You know, to answer that question, you know, there are companies now, serious companies, I mean, Bosch, Vaillant and others, you know, developing technologies that are going to be hydrogen ready, because you'll need a hydrogen ready boiler. Hydrogen burns slightly differently, and therefore it's you know, you need to do a little bit of variation there. I think that we would need to be at a point at which we have a distribution system for hydrogen. You know, I'm sure given a market, there would be some entrepreneurial folk who would come and do you a hydrogen top up. But that doesn't exist today as a business, right? I mean, obviously it does in an industrial setting. I mean, you know, Air Products will come and sell you some hydrogen. It doesn't sit in a residential setting yet.
Yeah.
So I suspect you're a little bit away. Someone did type in, what about biomass, into the chat. I think it cropped up, which I guess is another low carbon option. I'm sure you've looked at, but biomass boilers are also quite expensive, as I'm sure you've looked into. It's hard for me to give you a firm answer. I think that you will not be at the front of the queue, sadly, for these things, right? So it's going to be, I think, you know, your indicators are going to be when is there a rollout of hydrogen heating in, and these are going to be localized rollouts, right? So there was a big study. One of the best known studies in this area was the H21 study, which was a really nice piece of work that kicked off a few years ago the interest in hydrogen. And that was a paper study of converting Leeds, the city of Leeds, to run on hydrogen. That's not to say it will be first done in the city of Leeds, but you know, it's when a region switches to hydrogen, which means that the likes of Bosch and, you know, Worcester Bosch and Valent and others have got hydrogen boiler ready, and we've developed in volume all of the fittings and the service engineers and all of these things. Once that's there, then it can start to roll out, I think, more to people who are on the end of the network or off the network.
So it may happen, but it'll be quite a long wait.
I think, well, I fear you'd be, my guess is, right, my instinct is that you're not going to be front of the queue, because we've got to get the global supply chains developed. Now that it's happening, right? That's why the share price of some companies, including the one I helped set up, have rocketed, as the likes of Bosch have taken a stake in those businesses. So it is happening, and it has to happen if we're going to deliver on our 2050 commitments, right? But this issue of decarbonising heat is a really tricky and difficult issue. All of the options are expensive, and so there are, you know, debates about how you equitably do that. You know, you don't increase fuel poverty, but we can't continue to burn unabated natural gas. So it's got to go one of the two ways. So I guess my instinct says you are not, sadly, first in the queue, unless you felt so passionate that you were willing to be an early adopter, which might be quite an expensive experiment. So I think, you know, the technologies are being developed by serious players, which is good. But I guess they'll probably go into a kind of slightly more on-grid application first.
Yeah. Thank you.
Thank you. And Valerie is going to bring somebody else on screen, and it is Edward Lee, please.
Thank you very much. Yes, a really interesting, informative talk. Thank you. My question actually was about the problem that we face with the scaling up the renewables and nuclear. I mean, nuclear we can't scale up quickly enough. It's only to sort of meet a 50% decarbonisation by 2030. So we're very much reliant on scaling up renewables, principally solar and wind. And in order to be able to meet that sort of 50% decarbonisation, it seems really important that we exploit the efficiencies of electricity over petrol and diesel for the transport industry and gas for the space heating. But my worry is that if we are forced to use hydrogen, then we can't exploit those efficiencies to anything like that extent. So, you know, you mentioned a three factor COP for space heating, where there might only be 2 in the middle of winter. But if we're using hydrogen, and the efficiency of converting electricity to hydrogen and then back to electricity again means we're losing 50% of the energy, then, you know, we're not going to gain anything by then using the heat pump at the end. And similarly in the transport industry, if we're piping or carrying in trucks possibly hydrogen to refueling depots and then putting it in there, we're not getting the efficiencies that we would have had if we'd taken transmitted electricity and then used fast chargers at the sites. So I just wonder whether we kind of need to really focus on getting the efficiencies and the improvements in battery technology for all the applications where we can use electricity as a source, and really focus on hydrogen almost as a last resort for that for the storage, because that's kind of the only available option that we've got at the moment for the sorts of interseason or capacities that we need. So I only wonder if you have any thoughts on that.
Yeah, I mean, look, these are very valid points, right? And as I said, if we can use the electricity, we should use the electricity. There's no point making hydrogen if we don't need to, or if we can manage to not do so. I think the challenge is, so I think there are some more obvious places to think about hydrogen, and there are other places where hydrogen may come in, right? So I think for me, the areas where hydrogen competes really favorably against electric is heavy duty vehicles, right? So long distance transport, heavy duty buses I've mentioned, perhaps aspects of marine, perhaps some types of trains where it's just too expensive to electrify the line. Obviously, if you can electrify the line, electrify the line. In these areas, it's really quite difficult to see battery electric competing credibly, given where we are with our battery technology and where we think we're going to be going with it. Of course, if the batteries, if you do get amazing, perhaps surprising improvements in battery technology, then fine. So that's an application area where a hydrogen, a fuel cell electric, really starts to come probably through into its own. So that's an area where I would expect to see early markets emerge, especially with buses or truck or for things like point-to-point routes rather than open routes where you haven't got so much hydrogen infrastructure challenge in terms of putting in your refueling. I think the other area where I see hydrogen winning early, in the sense that it makes a good fit, is some of the industrial decarbonization issues. So if we already use hydrogen, of course, then let's decarbonize that hydrogen. So that's the chemical sector, fine. In some aspects of, in some areas such as steel making, and other areas where we need very high temperature heat, that might be where hydrogen provides a very good opportunity. If we're going into more biomass-based feedstocks for our chemical sector, because we're not going to be processing oil and gas into or oil into petrochemicals, we're still going to need chemicals, so we're going to more likely use more bio-derived chemical feedstocks, and bio-derived feedstocks lead more reducing power. So hydrogen is going to be probably part of that. And each of these are enormous markets, by the way. If we then start to think about, well, harvesting renewables, for example, the Saudi scheme in the middle of a desert, and there's also a thing called the Australian Renewable Energy Hub, which is in the middle of the desert in Australia, where they're planning to make green hydrogen and green ammonia in the desert and then ship that to point demand centers. Again, you're not going to do that with electricity. So all of these things are very important places where we can see the hydrogen sector starting to lift off. Now, when we come into smaller vehicles, light duty vehicles, it's not, it's not so clear to me where we're going to end up. I think it's going to be driven by consumer preference in part. It's also going to be driven by things like how much does the hydrogen cost? And the hydrogen costs are only going to come down if we start to see these other markets emerging for hydrogen and the cost of hydrogen coming down. So for me, it's not being driven by light duty transport, but light duty transport may benefit, right, from the technology. If consumers like hydrogen fuel cell vehicles because they can do 400 miles in one, perhaps they'll end up with a hydrogen fuel cell car and a battery electric car in the same, if they're fortunate enough to own two cars, depending on their circumstances. So I think that will be a consumer choice, right? So Jaguar Land Rover, for example, are quite interested in fuel cell hydrogen vehicles for their larger off-road vehicles because they're struggling to make it work with battery electric. But it'll come down to the price of the hydrogen and the consumer and what the consumer wants. I think the heating question is probably the most tricky one of all for me, which is that we have to switch off natural gas. And I just see a world in which we tell consumers that we're going to turn your gas supply off and you've got to have a heat pump to be a really difficult thing to sell. A world in which we say, you've still got gas. It's called hydrogen, but it's, you don't, nothing other than that is not different. And by the way, you can put it, or you can have a heat pump, or you can have a hybrid heat pump, right, which burns gas to top up your heat pump, or you can have a boiler. They're all low carbon. Which one do you want? Is a more tractable opposite situation. Now, the challenge for the policymaker and the infrastructure owner is how do you how do I look at the cost of that transition? But for me, if we don't put consumers into the picture, I just really struggle to see how we can make, because you can't go into people's homes today and tell them to, we're going to come in and a group of folk are going to come in and strip out your heating system and give you a new one, right? It's not, you can't do it. So people have to want it. And I think when we switched from, I am old enough to have been alive when we switched from town gas to natural gas, but not that old that I can remember it happening. But I've heard the stories, and with respect, Mike, you might remember it a bit more than me. That was a system. We lived in a different time, right? Consumers trusted government. Consumers trusted the energy industry. It was good for Britain. It was good for them. You came in and you did it, and everyone was happy, right? You can't imagine that happening today, where people don't trust the government, regardless of what colour of party they are. They just don't, and they certainly don't trust the energy companies. So it's a difficult one, isn't it? But I agree completely with your point on efficiency. If we can use the electricity, we should use the electricity. It's really about the role. It's about some of these difficult to decarbonize areas in the first instance, and then around heat. How do we provide options that consumers will move? Because you put in a heat pump, you do need to change all your radiators. So it's great in a modern build, the right thing to do. In a retrofit, it's not so clear. Anyway, I haven't really answered your question. Other than I agree with you.
A lot of sense there.
But it's a tricky one, right? I'm certainly not here to advocate for it must be hydrogen. I think we've moved past that point. It's really about what do these technologies bring to the mix, and can they add value? And I think that they can in the right areas. And those areas are significant. I mean, there are forecasts that say, well, 25% of world energy demand could be met with hydrogen. That is 75% being met with other things like electricity, but that's still something like $700 billion a year of hydrogen sales.
Nigel, we should let you escape. I've got a list of people who would like to ask further questions, but I'm afraid they're not going to do it tonight. I'd like to thank you. That was a super point to end on, actually. I think you've given us a magnificent view of the real potential of hydrogen, but also that it's not as simple, as you pointed out, as electricity or hydrogen. And as with many technologies, it's rather nuanced. And how do we get a balance of application depending on the context and application, and depending on the mix of alternatives available? It's been a complete eye-opener, extremely deep, but very accessible, very much in the best traditions of CSAR. So thank you very much indeed. It's been absolutely fabulous.
Right. Well, thank you for the questions, and thanks, Mike, for the invitation. Okay, that's it. I'll sign off. Good night.
Thank you. Good night, and good night, everybody. And we'll see you in a fortnight's time. Thank you.
Thanks. Bye-bye.